So we've already seen a couple different types of normal distributions in this module, and in this video you're going to see a third. We first looked at just a regular normal population with mean, mu, and standard deviation sigma. We next saw a distribution of sample means. We also called that the X-bar distribution, and we saw that that distribution was approximately normal as long as the sample size was at least 30. We also observed that in that X-bar distribution that the standard deviation was the standard deviation of the original population divided by the square root of the sample size. And the mean of that distribution was the same as the mean of the original population. Now in this video we're going to focus on a second sampling distribution, and that one is called the distribution of sample proportions. I also denote it p hat. And so a distribution of sample proportions is actually created in a very similar way as a distribution of sample means. It involves the process of taking a random sample from a population, recording a statistic from that sample, in this case a proportion, and then resampling again and again and again, and considering what would happen if we looked at all of the sample proportions from all of those different samples. And what it would look like is exactly what you see here. It would look like this p hat distribution, this bell curve. Now that is subject to certain conditions, and we're going to talk about what those conditions are in just a minute. But again, it just speaks to the fact that a normal distribution does kind of arise out of this sampling and resampling process. Now, in this distribution of sample proportions lies the true population proportion somewhere. Remember, statistics is all about, the course of statistics is all about using a statistic, a result from a sample, to speak about a parameter, which is the result from a population. And so if you had to guess where the true population proportion was in this distribution, where do you think it would be? Do you think it would be in one of these extremes? The true population proportion would be over here or over here? Or do you think it would be closer to the middle? And a lot of times people would expect it to be a little bit closer to the middle, and you would be exactly right. In fact, the mean of this distribution of sample proportions is p, where p stands for the true population proportion. So let's write this down. Let's say the mean of this distribution is equal to p, where p is the true population proportion. Okay, now the standard deviation of this distribution, it can be shown, is equal to the square root of p times 1 minus p divided by n. We're not going to get into exactly why this standard deviation formula is what it is. There are some connections, though, between this distribution and something called the binomial distribution, but we're going to be able to see that this can be verified through this simulator at the left. And then moving forward, we're always going to note the type of distribution that we have and then the means and the standard deviations of those distributions as well. Now I have to say, just like with the distribution of sample means, the distribution of sample proportions is not necessarily approximately normal unless you meet certain conditions. And those conditions here are the following. We need n times p to be at least 10, as well as n times 1 minus p to be at least 10. And so while these conditions seem a little bit different than the n is greater than 30 condition for the distribution of sample means, these are essentially ensuring a sufficient sample size just like above. Okay, so now I'd like you to look at this sampling distribution simulator at the left, and I want to just illustrate, in fact, that when we go through a process of taking a random sample, considering the sample proportion from that sample, and then going through if we go through that again and again and again, I want to show you that we do in fact end up with this distribution of sample proportions. So as we go through this, we can let me give you a little bit of context. Let's think about this as an example where we're considering the proportion of people in a population who are going to vote for a particular candidate in an election. And so let's say that the number of people that are in our sample, you could see over here at the left, our sample size is 100. Now let's pretend, and I know this is something that seems a little strange, but let's pretend that we know how everybody's going to vote in the population. And so where this says the true proportion of successes is 0.4, I want you to think of that as that is the true proportion of people in the population that are going to vote for the particular candidate that we're thinking about. So we're going to sample 100 people, and when we sample 100 people from the population, just because the true proportion of people in the population that are going to vote for our particular candidate is 40%, does not mean that our sample proportion is always going to be 40%. There's going to be a distribution. And so as you can see here, we're going to sample this 10,000 times, and when I press draw, you're going to see the result of this sampling and resampling process. So let's see how this plays out. So there you go. You've got this distribution that looks very much like a normal distribution. That looks like a bell curve. And on top of noticing that, I want you to look at the mean and the standard deviation in this table. And if the mean and the standard deviation in this table match up with the mean and the standard deviation that we were using on a theoretical level, then that just supports the fact that these are good formulas when describing a distribution of sample proportions. And so take a look at the first one. The mean on a theoretical level was supposed to be P, which is the true population proportion. And remember at the beginning of this, we said let's assume that we know that 40% of all people in a population are going to vote for a particular candidate in the election. So we assumed that the true P in the population, the true population proportion, was going to be 0.4. Experimentally, we see out of 10,000 sample proportions, the mean is 0.4002. And so that supports the idea that the mean in the distribution of sample proportions is going to be the true population proportion. Likewise, we could do this with the standard deviation, and you're going to see similar results. The standard deviation is theoretically is the square root of p times 1 minus p divided by n. And if we put this into the calculator, I can tell you what that is. So the square root of 0.4 times 1 minus 0.4 divided by 100, that is equal to 0.0490. And 0.0490 is really close to 0.0485. Again, just speaking to the fact that this standard deviation formula appears to be an effective one to use to describe the variation in the spread in a distribution of sample proportions. Now, we can also take a look at our assumptions, and typically you want to check your assumptions before you start working with the distribution of sample proportions and treating it as normal. But as you can see here in this picture, it definitely appears that we're working with a normal-like distribution of sample proportions. And so it's not going to be a surprise that our assumptions here check out. In fact, if we take n, which is 100, and we multiply it by p of 0.4, you get that is equal to 40, which is clearly greater than 10. And if you did 100 multiplied by 1 minus 0.4, that's equal to 100 times 0.6, which is 60, and that's greater than or equal to 10. And so that's not a big surprise, like I said, because we have a normal-like distribution. Actually, while we're at it, let me show you what would happen if those assumptions did not pan out. So let's go back over to the simulator, and this time I'm just going to tinker with the sample size a little bit. Let's pretend we had a little bit of a smaller sample, and in addition to a smaller sample, let's say that our true proportion of the population that was going to vote for a particular candidate was 0.2. And so what I'm doing is I'm trying to artificially create a result for n times p that violates this assumption. And in this case, if you had a 10 and you had a 0.2, then 10 times 0.2 would give you a value of 2, and that's clearly not greater than or equal to 10. And so I want you to see what our distribution of sample proportions would look like in this case. So I'm going to click on Draw, and it just confirms exactly what I'm talking about. That is definitely not a normal-like distribution, and that allows us to say that these assumptions are absolutely essential if we want to be able to state that our distribution of sample proportions is approximately normal. Okay, so that's pretty much it for this video, but I just want to wrap up with a quick summary. If we go back to the very beginning of this, I started talking about a couple of distributions, normal distributions that we had seen in the past. We talked about just a normal population, also a distribution of sample means, or the X-bar distribution, and now we're talking about the distribution of sample proportions. Moving forward in this class, it is going to be essential that you properly identify which one of these three distributions we're working with. So always ask yourself, is it a normal population? Is it involving sample means? Or is it involving sample proportions? Because as you can see, there are different means and standard deviations for each one of these. And so depending on the distribution that you're working with, you're going to have different equations that you're using to determine your means and standard deviations when we're using tools like normal CDF and inverse norm, which we're going to get back to in the next video. So let's take a look at some examples now.